Okay. And what are you going to do with that 44.12?
Well, you're going to wait to do some more pipette like we talked about, and then you take your volumetric flask and you put what you need in the volumetric flask. And then you add some H2O, distilled H2O, and then you invert it 20 times or until the NaSO4 is completely dissolved. And then using a pipette, you can fill to the calibrated line with more distilled H2O.
Very good.
And
Nice job.
thanks.
It's all for Jennifer. All right, good. Any questions on that one? Okay, what do we mean by a solvated OH negative? What do we mean by a solvated OH negative? Anna? Awesome. So it's solvated means that, well, actually we'll get back down here to this one here, so I'll just feed off what you have. So we have hydroxide, and then we're going to have the bottom part of the water attached or surrounding. Like that. So the hydroxide is being surrounded by the water molecules. Why did I not write the oxygen? Why did I not do this? Or can I do this?
You can't do that because the hydroxide has a slightly negative pull, and the oxygen side of the water has a slightly negative pull, and this like forces repel and opposite forces attract. So if you tried to put the two oxygen, or the oxygen closer to the hydroxide, it would repel, but if you put the hydrogens closer to the hydroxide, that like kind of pulls them.
Awesome, very good. So this would not have an attraction. This would actually repel. Okay, and then when we're talking about the water being polar, strong polar, so we have a partial positive or negative in, partial positive in. And what term did we say yesterday that you're going to see on the AP exam? So we're going to have the word Coulombic attraction. Coulombic attraction. Again, that just means positive, negative attract, like charges repel. Okay, we just tag a fancy word onto it. So we have something called a Coulomb's law that we'll get to later that talks about the charges, right, the charges between the two ions and the distance between the two ions. So there's an actual equation for this with the Coulomb's law, but you'll see this term Coulombic attraction throughout all the AP stuff, and it just means positives, negatives attract. Okay, sounds fancy. All right, what's the difference between dissolution and solvation? Dissolution and solvation. Anna?
Dissolution is the process of being dissolved, and then solvation is being like using water as not solving, the other one.
The other one. The solvent. Good. Yeah, so dissolution is the process of dissolving, so anything kind of breaking up, dissolving, and you can have different types of solvents. You can have hexanol is a good one, toluene's a good one, that would be from the organic side of it. Solvation is a process of dissolving, but when water is the solvent. And that's what we have mostly in organic, which is what we're talking about now. So most of, when you have the aqueous, so if this is Ag plus aqueous, it would be a solvation process. Water was used to dissolve whatever compound this came from. Okay, so we're just working on the terminology today. All right, good. Why is a water molecule a good solvent for both polar and ionic compounds? Don't think too hard on this. So we have well, methanol, okay, is slightly polar. And then we have NaCl, which is ionic. What's so special about the water? Okay. Yeah. So it's a, and I want to use this term strong polarity. And in the book we'll talk about like dissolves like. So ionic will dissolve ionic, polar dissolve polar, nonpolar dissolves nonpolar. However, the water is such a unique molecule because it's a strong polar, so not only can it dissolve polar molecules, it can also dissolve ionic because of the polarity. So if you look at NaCl example from yesterday, we talked about this ion is attracted to this ion, so there's our ionic bonding. And then we said that the water molecule all right, so this partial positive is almost a complete positive charge. Right? The electron is moved so much away from H that it almost has that complete charge. Not quite, but almost, but it's still partial. So because it's almost transferred, this makes this charge very, I'll use the word strong, so it can pull this away. Now, on a side note, how do we determine if water can dissolve this ionic compound? Maybe we have BaSO4. Maybe we have some, see, maybe aluminum phosphate, maybe. 3 plus, 3 minus. What determines if this is dissociated? This came up in a AP Bio question last week. Ooh, thinking question, okay. What's in your notes from yesterday? Corinne?
Doesn't it have to be ionic in order for it to dissolve it? Like a normal ionic.
Yes, but there are a few exceptions, which is what I'm trying to get at. So what determines if this water molecule dissociates that attraction?
Would it be like if like the strength of the partial or the polar bond, like the foreign charge, or I don't even know what to call it, like the charge of the H is stronger than like the charge of the NaCl, like the bond that holds them together, then would it dissociate them?
Perfect. There we go. High five.
Electronegativity.
What's that?
Electronegativity.
Yes, the electronegativity here. So the strength of the attraction between these ions, okay, has to be less than the attraction between the ion and the water molecule. If the strength of this attraction between these ions is greater than the attraction between the ion and the water molecule, then this will not dissociate. Okay? And you're going to see a little bit of that today when we talk about acid and bases. Next question, will C2H5OH conduct electricity? First recognize what is C2H5OH? Ethanol. Okay, so it's an alcohol. And would alcohol conduct electricity? No. Why? Yeah. No ions or charges to complete the circuit. Is CaCl2 a strong or weak electrolyte or a non-electrolyte? How'd you answer that one? Should we do some jumping jacks today, some push-ups? Chris has got the, what, no Mountain Dew today? You get the Coca-Cola instead?
No, I got Parents enjoy buying them those. But I got donuts yesterday from the farm.
Whole dozen? Morning.
Good morning.
Hey, what do you think? First of all, is it an electrolyte or is it a non-electrolyte? It is an electrolyte. How do I know? Ionic. Good. Ionic. Okay. Non-electrolytes are going to be your molecular compounds. Here we have the ionic compounds. Okay. Now, how do I know if it's a strong or weak? What do we mean? What do we mean by strong electrolyte? What do we mean by a weak electrolyte? So, definition of strong and weak. Corinne?
Strong electrolytes completely dissociate, and weak electrolytes dissociate partially.
Nice. Complete dissociation and partial dissociation. Okay? So because this is ionic, mostly it's going to be a complete dissociation. Okay?
How could you identify an ionic compound that would be, because the definition that I got this summer for a strong electrolyte says strong acid, bases, and like salts. So like, how would you know if you have an ionic compound that isn't strong?
That's a good question. Most of the time when we work with the compounds that may or may not be strong or weak, we're going to look at what they look like in a reaction. So if we see a double arrow, it's going to be a weak. If we see a single arrow, it's going to be strong. With that, okay? But I would say that 90-something% of your ionic compounds are going to be a strong electrolyte. They're going to dissociate completely. Okay. Now, to segue though, that brings us into this discussion: solubility versus dissociation. This is where sometimes we get a little bit of confusing going on. So, did you have time to talk with each other about this one? All right, I'll give you 30 seconds. Jackson, look on your notes, see if you can pull out what I was trying to describe yesterday. I'm not sure if I did a good job of that, okay? So 30 seconds, solubility versus dissolution.
Okay, I think you're getting the whole convenience. Yeah.
But then also to the dissolve.
No longer, so she started
Nothing. We went to work and I didn't talk to anyone who said it. I was like, why? So it's
Talk to anyone. It's kind of mean.
good. I work at Paint and Pot in Holland.
Paint a pot. Okay.
Yeah, it's like a pottery studio.
Yeah.
And no one came in last night, so I was just filling paints in the back all day.
Cool. Cool.
I didn't talk to anyone.
Oh, do you know what the paint is made up of? What chemistry?
No,
No.
but I'm sure we'll find out.
I don't know if it's latex or certain acrylic or
I think
certain.
it's acrylic.
Yeah.
Yeah.
Okay. It kind of hardens a little bit. With
Yeah.
The, yeah.
It gets all like crusty and all.
Yeah. Yeah. Okay. What'd you come up with? If something is soluble, what does it do? It dissolves, okay? So yesterday we had two substances that dissolved. We had salt and we had sugar, okay, that dissolved in water. Here I have an example of barium sulfate. So the dotted lines are my attractive forces. So we have the solid, okay? We're going to put it into water. And then when we put it into water and it dissolves, if it's soluble, what happens? Give it a shot.
If it's soluble, it will dissociate. So like the barium and the sulfate ions will be attracted by the poles of the hydrogen and oxygen atoms, and they'll be separated.
Okay. For barium sulfate, it's not very soluble. So, example of this solid, let's just say that we have this guy, and this guy are going to break off. Okay, so then we end up with this solid that is left over, and we have these compounds that are now separated. Okay, so barium sulfate is not very soluble. However, it is a strong electrolyte. So these compounds then in water are going to separate completely. Okay, does that make sense? Solubility versus solvation or just dissolution. Solubility is explaining the extent to which the compounds break up from each other. Okay, dissolution is the extent to which the compounds break up from the finiteness, the ions or the molecules themselves. Okay, makes sense? And then the term electrolyte means that it's going to form ions so it can conduct electricity. Okay. Okay, good with that? All right. And let's do a quickie on acid and bases. All right, so HCl is a common acid. What's the name of HCl? Okay, hydrochloric acid. And I put aqueous next to it, so what does that mean? It's in solution. So when we did the double replacement reactions, we did ionic equations, what would this look like then from the ionic standpoint? Well, I'm just giving you whole hard questions today, all right. All right, figure it out. This is one of the exceptions because HCl looks like a molecular compound, okay, but it's one of the acids are one of the exceptions because they're actually ionic in nature. So aqueous would mean ions in water, okay. So how would you rewrite what do I have up there? What does that look like? Kitty? And perfect. Very good. Okay, awesome. So what happened to my H? How did it become? Maybe I'll hold that thought. We'll come back to that one. So by definition, we're going to say an acid is a proton donor. It's being oxidized in this case, losing electrons. So if you have an H atom, back to Gen Chem, H atom. So it has atomic number 1, so it has 1 proton. What's the mass number of hydrogen? It's also 1. Okay. And it's neutral. So if it's neutral, how many electrons does it have? 1. So how does it become an H positive? What's that? Yeah, gets rid of the electron. So what happens then, it becomes, all you have left is a proton. Okay? So we say that an acid donates a proton. Oh, that's your H+. There are 3 types of acids. We have the Arrhenius acid. This is what we call the Bronsted-Lowry acid. Then we have Lewis acids. Lewis acids are probably the more preferred definition and a way to look at it, but you really won't hit that until sophomore year in college with that type of insight, if you will. So right now they decided just to focus on Bronsted-Lowry acid for Gen Chem, okay, or for freshman college class. Okay, so all acids are going to donate a proton. So how do you recognize that? On the product side, you should see an H positive someplace in there. Okay, so that's a quick way to identify an acid. Now, aqueous means water, right? So water has this structure. And remember, we talked about these lone pairs being high-density electrons. Okay, those high-density electrons are going to attract the proton. We're going to end up getting this structure. This is called a hydronium ion. And the hydronium ion is basically responsible for the solution being acidic. The H plus is just a shortcut that chemists use. So to be accurate with this, we would write H3 positive here, H3O positive here, okay? But we take a shortcut and we just put H plus. But this is the real deal. This is what is really happening, okay? So the more H pluses or more hydrogen ions you have in solution, the more concentrated the acid. Okay, usually the more concentrated the acid, the more powerful the acid is. Okay, doesn't necessarily mean if it's a strong or weak acid. We'll talk about that in just a second. Okay, so the acid properties depends upon how many H pluses we have in a solution. Okay, the more concentrated of this, the more potent, I guess you'd say, the acid is. Okay, so we have different types of acids. We have a monoprotic acid. Monoprotic acids. Protic referring to protons. Mono referring to 1. So these acids are going to donate 1 proton. Okay, so So we have HCl would be a monoprotic acid. We have HBr, monoprotic acids. We have acetic acid. What else do we have? HClO acid. So you recognize that there's one H that can dissociate or be produced. We have diprotic acids. This is really tough. Diprotic acid, what's that going to mean? Kim is giving me the peace symbol. All right, stay calm, treat him like a friend. I got it, yeah. All right, so diprotic acid would be like sulfuric acid. Okay, it would be diprotic acid. In biology, you talk a lot about carbonic acid. So we'll throw a little biochem stuff in there at you. Okay. And then we have triprotic acids. So we might have ingested some of this morning with your breakfast maybe. Any ideas what a triprotic acid would be? C6H5O7, citric acid. Remember the citrate ion? Okay. In your pop there, you probably look there, Chris, too. You should have this in there. A little phosphoric acid. Okay. What's that? Is it in there? I know Dr. Pepper has a lot of it.
Phosphoric acid.
Yep. There it is. Nice. Yeah. So phosphoric acid, most of the time it's used for more of a preservative. Okay. But when you ingest it, this is what blocks your senses in your digestive system from your stomach saying, hey, way too much sugar, better stop drinking. And this blocks that so you can keep chugging. And so you know, I don't know how much sugar's in that.
A lot.
There's a lot. Yeah. So you a lot. I drink it just for the caffeine.
42 grams.
Yeah. So some people will go to the diet because it still has the caffeine in it, but it doesn't have the sugar in it. You know, we'll have like a saccharin or maybe a sugar substitute. What's that? And then it has some of the carcinogens in it. Is it the saccharides? There's a fake sugar that they try to use in there, but I don't remember. Yeah, I don't remember. They change so often with that. So, but it's interesting that you know, we're a beverage stuff. I understand, you know, it's got a nice little kick to it, a little fizzing from the carbon dioxide and that sort of thing. But again, this is telling your stomach you don't recognize that somehow the neural pathway to your brain doesn't say, hey, we have too much sugar. You're going to feel sick here, right? So like if you eat 15 ho-hos, did I tell you about my Amazing Race experience with my wife? Didn't I tell you that last year? I didn't tell you that last year? I cannot eat ho-hos to this day because I get sick just looking at them. No? Okay. So my church puts on this activity called the Amazing Race, which is just like the show, the Amazing Race, okay? So one year they had it as an indoor, just an outreach type of thing, an indoor thing. And so my wife and I, and then we partnered up with another couple, and we had to do all these activities and so forth together, and that's just like the Amazing Race, solve riddles and that sort of thing. Well, we went into our room, it's our third challenge, and we walk in, and they say, okay, you guys sit down. So we sit down, and then bring out a covered plate, you know, with a lid over it, you can't see what's in it. And so they said you can sit where you're at or you can change places. So we kind of changed places a little bit. So the task was that wherever you were sitting and you open up the lid, that's what you had to eat. They were nice, mostly, okay? But there was a time frame to it. So you were given a certain amount of time for it. and you had to finish everything. So if you didn't finish your food item in a certain amount of time, then you got a penalty deducted, and somebody else on your team had to finish it and that sort of thing. Okay. Well, my wife hates cheeseburgers. Guess what she got? 5 cheeseburgers from McDonald's. Guess what I got? I got Ho-Hos. Sweet, you know. But there were 5 of them. So 2 times, that's 10, because it's 2 in a package, okay? So, oh, I can do this. So you're eating, so I eat one, eat another one. Oh, okay, not too bad. Eat 1, eat 4, okay, halfway done. Eat 5, eat 6. So all that sugar goes into your stomach, right? It has to go through a combustion reaction in your digestive system, so forth. And now you're starting to feel sick. Like overeating Halloween candy. Okay, times 10. It was terrible. So by the time I got to 7, 8, I'm feeling sick and nauseous. And you didn't have anything, you couldn't drink until you were done. So you really couldn't wash it out too much, whatever. So you get that burning, just throw up feeling in your stomach, nauseous feeling in your stomach, okay? Because there's too much sugar in there, right? Your body needs to process all that, and you eat too much at once. So that's what's happening with the pop, though. There's a ton of sugar in there, but this phosphoric acid is preventing your body to recognize that there's too much in there.
Did you ever slow it down?
I didn't. I got it done, but it was past the time frame. My wife ate 2 of the 5, so I'm so proud of her. And then I can't do it. So we lost some points on that one, but we had other people with us that, one guy had 4 or 5 pieces of pizza, slices of pizza. So they're just, good, yeah. Anyway, so I can't eat those anymore just because I just have that connection, that memory. I'll get sick just thinking about it.
There's like a psychology term for that. Like if you get sick on something and then you don't want to eat it, like because it tastes bad or like the thought of it makes you.
It's like a hypnotic type of thing where it just brings back the memories and you get the same, Ooh, thanks for the memories. That was good stuff. Okay, so we have acids that are monoproduct, diproduct, and triproduct. So it's how many H's that they can dissociate or how many protons that they can release, okay? Now, if we look at a diprotic acid, and I'll pick sulfuric acid to begin with. Okay, now FYI, most of the time you're going to see with acids and bases water as another product, but a lot of times books will take shortcuts and just skip that. It's just understood that that's always there because of the aqueous. Okay, so you might see this plus this, then the arrow. You might just see this and the arrow. Okay, so they assume that we already know it's in water. Okay, so the thing we have to understand, though, is with acids, it can only deprotonate, ooh, good word, deprotonate 1 proton at a time. Okay, so this is going to break down into our hydronium ion and HSO4 negative. And then this HSO4 negative will go through another side reaction, and it will break down into our sulfate ion. However, for sulfuric acid, this reaction is reversible, meaning that here we have a complete dissociation. Here we have a partial dissociation. So in the solution, overall, we have hydronium ions. We have this ion, and we have this ion. So we have 3 species in our acid. Okay, this may or may not come into play, depends on the reactions that we do. Okay. All right, so if we get into a little bit of organic, here we have acetic acid. This is also acetic acid. This is more of the organic way of writing it. This is the more condensed way of writing it. So we see the H and we see the acetate ion. So we see the 2 separations here. Here, it's kind of hard to see that. Okay. On your polyatomic ion sheet, did I have this on there? Did I have this on there? I changed it over the years. I don't remember. I think I have this on there. So we used to write it this way, and then I put both of them on there, and then students got confused, so I just went to this way for Gen Chem. This one here? Okay. So if I were to write this out, we have CH3, so there's my methyl group. Okay, and I kind of like the organic way because it kind of helps me picture what the structure looks like versus this. So there's my CH3. And we have a carbon. That carbon is double bonded to an oxygen. This carbon is bonded to the oxygen and hydrogen. So this acid has 4 H's. So why isn't it not quadprotic acid? Quadprotic acid, that sounds kind of cool. This is a tough one. I don't know if you can answer this one quite yet. Okay, yes, you have an idea? You're saying that the OH is going to come off? Okay. All right. You're kind of on the right track. If this OH was attached to a metal, then that would be okay. But then we would have a base instead of an acid. But you're thinking kind of in the right direction. Okay. Let's look at, this is something totally new for you guys. So let's look at electronegativity again. Okay. On the periodic table, which is more electronegative, carbon or oxygen? Oxygen, okay. So oxygen here then is pulling, so we have these high density areas here. So oxygen has an attraction, so the electrons are kind of being pulled this way, okay, from carbon to oxygen. Okay, and also being kind of pulled this way because they're fairly close, and this is high density here. What happens is that this area here is pulling the electrons from each other, which weakens the attraction between the O and the H. And then the H can come off. Carbon and H, carbon has an attraction, so it just kind of pulls electrons through it. It has a pretty strong attraction to those H's. They're not going to dissociate, okay? But this OH part will allow the H to come off because the attraction weakens with that carbon. Yeah. Yeah. So it can only release this H. These H's are not able to break apart. Okay. Okay, when we hit the acid-base unit, we'll come back to that. Okay, there are 7 strong acids. What do I mean by strong acid? Same thing as a strong electrolyte. A strong acid would be what? If you have a strong electrolyte, what does that mean? Completely dissolves. If you have a strong acid, what does that mean? That there are only 7 strong acids. There are only 7 acids that would completely dissociate in water. So whenever I have an acid here in water, it's going to be a single arrow. So if I have 5 moles of acid here, it's going to completely dissociate into 5 moles of this and 5 moles of this. I won't have any of this left over. That makes sense? Okay, so here are the 7. Most of them are monoprotic. You want to memorize these 7 because when we start using them in chemical reactions, we want to know if it's strong or weak. It makes a big difference. So HCl is one. The name of HCl. Hydrochloric. HBr is another strong acid. What's the name of this guy? Hydrobromic. HI is another one. Hydroiodic. And then we have HClO4, which we talked about earlier. It's an oxy acid, oxyanion acid. This is perchloric, okay, perchloric acid. HClO3, and this is chloric acid. Right, so we have perchloric, chloric, chlorus, and hypochlorous. Remember the oxyanion acids, okay. So only 2 of those are strong with the more oxygens. The chlorus and the hypochlorous are not strong acids, okay. Then we have the fun ones. We have H and O3. Nitric acid. Nitric acid does not like metal at all. Any metal it just doesn't like. Nitric acid with copper penny, really cool to watch. Okay, but it will release nitrous oxide, which is a brown haze gas, and it will kill you. Very toxic. Okay, so we don't want to do that. We can do it in the fume hood, because then it goes to the English room. Ha ha ha. We should put laughing gas in there.
There we go.
No? What's the train of thought? Yeah, 1, 2, 3, 4, 5, 6. Oh, and then the only here's the word, polyprotic. What does the word polyprotic mean? Many. So the only polyprotic strong acid is sulfuric acid. Okay. Yep. Okay, so a base is going to be a proton acceptor, so just the opposite, proton acceptor. And from that, it's going to produce the hydroxide ion. The hydroxide ion. So the hydroxide ion is responsible for the basic solutions or basic characteristics, like soap is very slimy and slippery. Okay, that's a high pH. So that's responsible for the hydroxide part of that. KOH is another example. CaOH2, another example. So you notice that they all have the hydroxide ions in the compound. So that's a pretty good way of distinguishing if it's a basic compound or not. there are some substances like NH3. What's NH3? What's that? No, not nitrate. No. Ammonia, not ammonium. That's NH4. Yeah, this is ammonia. So if you use Windex, a window cleaner has a little bit of the aroma or smell to it. That's the ammonia that you smell. Okay. Ammonia, when it mixes with water, forms the ammonium ion and hydroxide ion. So it's taking an H away, and then we end up with the hydroxide. So we have some substances that do not have the OH in it. That is considered a base because it's producing the hydroxide on the reactant side. All right, a couple more minutes here and we'll finish up. All right, so we have strong bases. By the way, for the strong acids, anything that's not a strong acid, any other acids are considered weak acids. Okay, if it's not part of the 7 group, the fancy 7 group, all right, the Magnificent 7, I think that was a movie. Okay, if it's not part of the Magnificent 7, the rest are strong weak acids, okay? All right, so for strong bases, we have the alkali hydroxides. So group 1A hydroxide, so anything group 1A would be a strong base. Okay, sodium hydroxide, lithium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. Anything for the group 1A hydroxides. Okay. For group 2A, we call them heavy group 2A hydroxides. So heavy meaning the mass of the nucleus. And here we're going to have calcium hydroxide. We're going to have strontium hydroxide, and then barium hydroxide. Okay, so those are considered strong bases. Okay. There's some other ones too. We have, sorry, I won't give you too much. So we have oxides, metal nitrides are also strong bases, but we'll get into that when we get to the other unit. All right, let's finish up today then with neutralization. So when we have an acid-base solution, we want to neutralize the acid or neutralize the base. So we end up with a solution that is not acidic or basic. It doesn't have the H pluses or the OH negatives. It doesn't have certain properties of either one. So a basic one would be HCl, strong acid, NaOH, strong base. We end up getting HCl aqueous plus H2O. Okay, so making water here. Now here's the key. This compound is called a salt. Okay, now, we think of salt as table salt and so forth, and this one is, okay? However, in the chemistry world, a salt is a byproduct of an acid and base reaction. Okay, so that compound of the ions that we end up with, we label it as a salt. Okay, so be careful with that one. And lastly today, something cool. I think I talked about this last year. Actually, we talked about with double replacement reactions. If we were to rewrite this as ionic, we have this. Okay. These ions neither have acidic or basic solutions. They don't do anything in solution. Remember, we're going to call these spectator ions. Okay. And spectator ions are always going to, not always, but spectator ions will derive from a strong acid or a strong base. So any of the ions that come from a strong acid or strong base are always going to be a spectator ion. Okay, very important that we get that. Any ion that comes from or derived from a strong acid or strong base is a spectator ion, which means it's going to be negligible in reactivity. So in other words, they're not going to react with anything. They're just floating around, not doing anything. So if that's the case, then all we have is water. If these ions aren't going to do anything, then all we have is water. So we have a dud. We have no cool thing at the end. Now, if we evaporate the water, then we get the solid salt and stuff and put it on your steak or whatever. Ho-hos, it makes it taste better. A little mustard, the mustard on the ho-hos, you know. Just trying to get that experience out of my head. So, okay. So tomorrow we're going to finish up with redox reactions, so maybe 20 minutes to 25 minutes or so with that. I think that would be enough for that. Your job tomorrow then, after that, is if you have any questions to go over things that we've talked about, and then plan on having our test on Thursday. Okay? And then we'll get into actual new stuff, get into the labs, and start rolling here.
Does the acid and basis stuff line up with the like hydroxyl and the groups and stuff like that, with how they like break apart and all that? Biology or not really?
No.
No?
No.
Okay. That just happened to be the example was similar with like that.
Right. So you're talking about the functional groups here.
Yeah.